Alright, thanks for coming to watch lesson 6.4. We're going to look at some really key ideas today. Really key ideas. Something called the definite integral. And you're like, we've done that, didn't we? No. We did the indefinite integral. Okay? I'm also going to show you how you can use the calculator to do some integration. And then, hey, this is important because it's called the fundamental theorem of calculus. Okay? So, really important concepts. Pay attention. It's really important. Okay, let's think about this definite integral. Now, before I do that, remember or recall that an indefinite integral looks like this. The integral of, and we've got a function, dx, and that's it. And when you do something like this, you always get another function, and then you have to put the plus c. Whereas a definite integral looks very similar, except now I've included these upper and lower limits, and they're attached to this integration sign. Okay? And when you do this, you no longer get a function, but you actually get a value, a number. Okay? The value can be thought of as something called signed area from the lower limit a, usually a left side boundary, to the upper limit b, a right sided boundary, between the curve f of x and the x-axis. So let me draw this now for you. Okay, a definite integral. You can draw this out if you want, or just enjoy the show and watch. The integral from a to b of some function f of x dx. So if I were to draw this out, okay, got my function f of x, my left boundary a, my right boundary b, and then the definite integral will just be the signed area. So in this case, this would be positive because it's above the y-axis, and that would be the answer. Okay, whatever that area is equal to. Now, I did say it could be positive. Yes, it could be negative, right? If it was negative, you get a picture like this. The graph is below, right? A, B, this area here is negative. Or it could be 0. You're like, 0? How can that be? Let me show you. How about a graph like this? Here's the starting A. Here's the ending B. Got a triangle here and a triangle here, and both of those are the same. So a positive area that's the same, adding to it a negative area that's the same. Yes, the resultant is 0. Okay? And the key thing I want you to understand is that when you do a definite integral, you get a number value. When you do an indefinite integral, you get an expression or a family of curves. Okay, so an indefinite integral, family of curves, that's why it's the plus c. Definite integral, an actual number. So when you're looking for an actual number, then the calculator can actually do it for you. So a TI-84 or 83 calculator can be used to find the value of a definite integral. Okay, there are actually two ways to do it, and I'll show you both ways. There's a way in the calculate menu where you graph it out, or there's a way that you can use something called FNINT in the math menu. Okay, the calculate shows a graphical representation. If you like pictures, that's great, and it represents signed area quite well because you can see if it's positive or negative on the picture. So let me show you that first with examples 1, 2, and 3. If you can pull out your calculator, okay, and I'd like us to go and turn it on. Go to the calculate menu, which is in the graphing screen, and so what I'd like us to do is actually go to y equals to first and actually plug in the equation. So our equation here is x cubed minus 6x. Notice what happens when I just graph it out on the standard window coordinates. So x min of negative 10, x max of 10, and same thing with the y min, y max. A nice cubic function. Great. Now if you go to the calculate menu now, which is the second function trace button, notice that if you choose number 7, it says integral f of x dx. That's what we want. And now it says, give me the lower limit. So where should I start on my left boundary? Well, looking at my example here, it's actually negative 3. So let's plug in negative 3. Press enter. Then I'll say, okay, where do I want to stop? Well, where's my right-hand limit? That would be the higher number. That would be 1. Press enter and watch what happens. It actually does the signed area for you. It visualizes it, and it tells you that the net result of all those negative pieces and that large positive piece is the number 4. So that's your answer, 4. Okay? All right, you go try number 2. So back to my calculator. Okay. This time I'm going to calculate again, because it's the same function. Choose number 7. Lower limit of negative root 6. Upper limit of root 6. Go ahead, do that, and wait a minute. Oh, I forgot to clear it. Oh, I'm so sorry. Let's try this again, because I want you to see the visual representation. My bad. So once again, graph it out. Okay. Now we'll go ahead and do that again. Choose number 7. See, practice, right? Practice makes perfect. The lower limit's negative root 6. Press enter. And then the upper limit is positive root 6. Press enter. Notice now why the signed area is 0. Yeah, you've got the two like bumps. The one that's positive above the x-axis, that area is equal to the one below the x-axis, so the net result, of course, is 0. Okay? Now, how about number 3? I want you to try this with the absolute value. So, if you want to try this yourself before watching me do it, by all means, press pause. If you do want to watch me do it, then keep rolling. So now, go to y equals 2, find the absolute value, which is under the math menu. Go right to num, choose number 1, abs, x cubed minus 6x. We will graph this out. Notice that, yes, everything is now above the x-axis. And now, similarly, we'll go to calculate number 7, and I'll choose my lower limit of negative 5. I'll choose my upper limit of 5, press enter, and da 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 da. Wait. Oh, here it comes. Whoa! Wow, 198.501. 3 decimal places for the AP exam, remember that. Okay? Now, that's using what we call the calculate menu. You always get a visual representation. Now there's also another way of doing it called the math menu, and we can use that. This method only provides the value. It doesn't actually give you a picture, but that's usually what we need anyways. We don't really care about the picture. Now I want you to know that the math menu also gives a more accurate answer. Okay? And the math menu uses this notation FNINT. Okay? And this is actually what's recommended for the AP exam and all the problems from now on. Not the actual calculate menu, but the FNINT. Okay? So let me show you where that is, and we're going to do question number 4, which is exactly the same thing as number 3. Okay? If you have a TIA3, then the syntax you're going to see is something like this. It's FNINT, and the first element here is the actual function. The second element here is the variable, so you type in x. The third element is your lower limit. And your fourth element that you need to put in here is your upper limit. For those of you who have the TI-84, then I think you can actually put it into a notation that looks like what you actually write out. So I unfortunately do not, so I have to go and use this FNINT stuff. Where is this? It's under the math menu, so once again press math, the button under the green alpha key. You're going to have to scroll down to number 9, that's your FNINT. And now let's type in the actual expression, then the variable, then the lower limit, then the upper limit. So the expression, math, choose num, choose number 1, x cubed minus 6x, close the bracket. Now you have to put a comma separating your inputs. The next thing is the variable x, so just type in x, comma, and then now your lower limit, -5, comma, +5. Close the bracket. Press enter. Do, 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 do. Do, 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 do. Ah, here we go. 198.50. Ooh. Wait a minute. The answer is a little bit different than the previous one. 198.501. This is 198.500. Uh-oh. A little bit of difference. And that's why I said the math menu actually gives a more accurate answer. The one that's a calculating menu, they're actually using the picture, and you know, that previous picture had some pixels perhaps, and it didn't really touch the x-axis perhaps in some places, so there's a little bit of an error. I would like you, once again, to note that this is the more accurate answer. This is the more accurate answer. Okay? And for the AP exam, this would be the actual correct answer. They would actually mark that one wrong. So please use the math menu when you're doing AP exam questions. Okay, enough with the calculator. How about number 5 now? We talked about the definite integral as signed area. Signed area. So if I ask you to evaluate this definite integral, why is this called a definite integral again? Because I have limits here, without using the calculator, what would you actually do? Well, can you draw a picture for me of the function absolute value of 2x minus 1? So if I were to actually draw a picture, hopefully you remember this is the V-shaped graph, and it actually touches right here at the point. Well, that's when y equals 0, so 2x minus 1 equals to 0, 2x equals to 1. Did you remember that x equals to a half? Yeah. And if I'm looking at signed area, I'm saying I'm starting at the left limit of 0. So I'm starting at 0 here. And I'm going all the way to 3. And so you're trying to find the signed area. Notice that the two shapes that I've drawn are two triangles. One smaller one and one larger one. I just have to add them together. Now, what are the heights of these triangles? Well, this height here is at when x is 0. So if I want to plug in the value of 0 into the function, 2 times 0 is 0, minus 1 is -1. Absolute value of -1 is 1. So I know this must be 1 as the height, and this is a half. The length of the right triangle here is 2.5. And if I were to figure out the height here, plug in value of 3, 2 times 3 is 6, minus 1 is 5. So, time to do some basic geometry. Base times height divided by 2. Base times height divided by 2. And if I were to simplify that, that's a quarter plus, what's that, 6.25, so 6 1/4. A quarter plus 6 1/4 is, I think, just 6 1/2. There you go. And this is the answer to the definite integral. Remember, the answer to a definite integral is always a value. Okay. Now, what if I go the other way, where I give you a picture now for number 6, and I want you to set up the definite integral. So I want you to write something like this for me. Okay. So I've got this function. I want to go from 0 to 2. So hopefully you can see that I'm integrating from 0 to 2. There are my limits, my left and right limits. The function itself is just 2x squared minus 3x plus 2. And then don't forget my dx. If you wrote that down, you are correct. This is the definite integral that represents the shaded area. Yay! Okay, so that gives you an idea what a definite integral is. Now I want you to use that idea with everything else you've done to discover what the fundamental theorem of calculus is all about. Okay? So we're going to use 7, 8, and 9 to help us discover what this thing is. And to do that, I want you to answer 4 parts to every single question. Okay? So let's do 7 together. Notice that for number 7, my function is now this derivative. So the derivative is my function. It's f prime. And this function seems to be a nice horizontal line. So if I ask you to do the following, find the definite integral from 0 to 5 of the derivative function. Visually, that means I'm taking, yes, the left limit, or lower limit, upper one, which is the right bound, and I want us to find the area of this region. It so happens to be a rectangle, thank goodness. So the area is just base times height. Did you get 15? I did. Good. Now let's do parts B, C, and D now, okay? So part B says, can you write an equation for f prime of x? Well, this is just a horizontal line, so yeah, I can. It's just equal to the value of 3. And then in part C, I'm saying, well, can you find the actual function f of x? So given the derivative, can you find the function? Can you say find the antiderivative? Yeah, you can. So how about me doing this? The integral of the derivative dx. The integral from the derivative, well, this derivative from part B is just the number 3. I can take the integral, that's 3x plus c, but look, look, look. Here is a point on the curve where the x value is 1, the y value is 4. So this is like the initial condition. We can solve for c, so c equals to 1. And therefore, what we have now is, yeah, f of x is equal to 3x plus 1. Cool. All right, all that stuff we did from before, the initial condition from lesson 6.1. And then finally, in part D, can you find out what f of 5 minus f of 0 is then? Well, that's nice because now I actually have the function f of x, so I'll quickly just use it. So I'll use my answer from part C. F of 5, of course, is just 3 times 5 plus 1. That is, what, 16? And then f of 0, what's that? Well, that's 3 times 0 plus 1. That's 1. So, therefore, f of 5 minus f of 0 is just 16 minus 1. That is 15! Cool. Okay. Can you try number 8 then? Because number 8 is very similar to number 7. Alright? So I want you to try 8 yourself, and then once again come back and double check your work with me. Press pause. Okay, I hope you're done now. If you're one of those people that just always doesn't press pause when they say press pause, you're losing out. You're messing up your own learning, I must say. Okay, here we go. Part A. Visual from -2. Ooh, that's a triangle to 1. Ooh, another triangle. Notice that the triangle has a height here that is negative because it's below the x-axis. So I'm thinking 1 times -2 divided by 2. And then the other one here, 2 times 4 divided by 2. Add those up, that's -1 plus 4. I think the answer is 3. Did you get that? This is a line. Looks like the slope is 2. It has a y-intercept of 2. There's f prime. Figure out f of x. Okay, that's just the integral of 2x plus 2. That becomes x squared plus 2x plus c. We will plug in the initial condition to solve for c. Did you get c equals to -3? So therefore, f of x is equal to x squared plus 2x minus 3. Did you get that? And so now if I want to do f of 1 minus f of -2, I'm just quickly plugging 1 into the expression. That's 1 squared plus 2 times 1 minus 3. Take away, put a big bracket around here, plugging in -2 all squared plus 2 times -2 minus 3. What does this equal to? 1 plus 2 minus 3, that's 0. Oh, nice. That's 4 minus 4 minus 3, that's -3. So 0 minus -3 is +3. Nice. Okay. Did you get that? If you did, great. I'll do 9 with you, okay? Alright. Position. Displacement of the object. Remember, the displacement is just a difference in the position, so x of 4 minus x of 1. And if I calculate that, let's see what we get. -1/2 times 4 squared plus 4 times 4 minus 3. That's the first part. I always like to put a big bracket around the second part so I don't get messed up. 1 squared. What do I have here? 8 minus 3 is 5, I believe. So that's 5. And then over here, 4 minus 3, 1, I think it's 1/2. So 5 minus 1/2 is just 4.5. 4.5. Okay. Alright. Part B. Hey, find the velocity equation. Okay, well, the velocity is just a derivative of position. I can do that. -t plus 4? Yeah. And then part C says sketch the graph. I can do that. This is a, I hope I can do that. Y-intercept of 4, slope is 1, 1 down, 1 to the right, 1 down, 1 to the right, 1 down, 1 to the right, 1 down, 1 to the right. Whee! Oops. I didn't draw that very well. Whee! And then now, if I asked you to find the integral from 1 to 4 of v of t dt, v of t is the function that I graphed in part C. Going from 1 to 4 would be from 1 here all the way to 4, just that nice little triangle. Base of the triangle is 3. Height of the triangle is 3 divided by 2. Look at that, that's 4.5. Nice. Woo, we've done a lot of math. Let's take a break. Whoa, let's not take a break because I want to keep going. But let's just review from 7, 8, and 9. Okay? Do you notice anything about the answers to A and D? Parts A and D? Part A, Part D. Ha! Part A, Part D. Ha! Part A, Part D. Ha! Yes, they are the same. Now, don't just look at the answer now. Look at the actual question and see what connection you can now make. Let's go back to number 7. In part A, I asked you to find the definite integral of some derivative function. And in part D, I said take the actual original of that function, or the antiderivative, and then plug in, look at that, plug in 5 and 0, plug in the limits. So from number 7, oops, that's not good. From number 7, what you've told me here, and you can write this on the side if you want, I'll put in a little bubble. You've just told me that the integral from 0 to 5 of f prime of x dx is the same thing as f of 5 minus f of 0. Is that the same in number 8? I hope so, because look at this. Definite integral of derivative equals to the function plugging in the values of the limits. So notice that once again, the integral, or the definite integral of a derivative equals to the actual function evaluated at the upper limit minus the lower limit. Is that the same for number 9? You bet it is. Here we go. The integral from 1 to 4 of the velocity function, that is a derivative, is equal to the position function evaluated at the upper limit minus the position of the lower limit. So what does this give rise to? Please turn the page. Haha, it's in a box. It's really important. It gives rise to something called the fundamental theorem of calculus. If you have f prime and it's a continuous function, then the definite integral from a to b of f prime is just equal to, and I prefer you use this, f of b, so the original function f, or the antiderivative of the f prime, f of b minus f of a. Now some textbooks have used this notation. This notation is exactly the same as that. This is the function f of x, and then that bar means you want to evaluate from f of b to f of a. Okay? This relationship is known as the fundamental theorem of calculus. It's so fundamental that I'm going to make you write it twice. F prime of x dx equals to f of b minus f of a. Okay? Fundamental theorem. You've got to know it. It's fundamental. Okay, so let's try actually using it now to evaluate some definite integrals. Okay? I know, not a long video. You're like, oh, he talks so much. Don't forget, in lesson 6.2, I gave you like a 6-minute video. Okay? Things balance out in the end. All right, number 10 here. Here we go. How do we do this? So think about this as the derivative. So I need to find the antiderivative now. So remind yourself that root y is the same thing as 1/2. So when I do the antiderivative, I can then take the 2. I can then do antiderivative, so add 1 to the exponent, 3 over 2, divide by 3 over 2, or multiply by 2/3. And then the antiderivative of 1 is just y. Now, do we need a plus c? We technically actually don't, and I'll show you why. Okay, so why don't you just put down your pen right now and just watch me for a sec. Okay, our goal after doing this is to then evaluate. So I'm going to use that notation, plug in 0 and 4. We always plug in the upper limit first. So look at what we have. That's 4/3, 4 to the power 3/2, plus 4 plus c. That's what we do. Okay, that's the upper. Now we're going to subtract from it the lower. So we're going to plug in the lower. 0 plus 0 plus c. Notice what happens to my plus c's. Yeah, it's a constant from the front, constant in the back. We're going to subtract them. Guess what? They just become 0. So really then when I do a definite integral, I don't need that plus c here anymore. Okay? And once again, remember, the definite integral gives you a value, so we're not looking at a plus c. We're not looking at a family of curves anyways. So once you have this done, ignore the plus c now and just write down going to evaluate from 4 to 0. And then now, once again, just go ahead and evaluate this. So this becomes 4/3 times 4 to the 3/2 plus 4 minus, of course, 4/3 times 0 plus 0. Well, that just gives me whatever I had there. So I'll just write this as 4/3 times 4 to the 3/2. That's the best I can do for an exact answer anyways, plus 4. And there's my answer. Okay, that's using the fundamental theorem of calculus. Alright, let's try 11. Not so easy antiderivative this time. Yes, this is the one where you have an extra factor. So if you like that reverse chain rule or you like u-substitution, doesn't matter. I'll show you both. Okay. If you do reverse chain rule, then what you need to do is find the derivative of the inside function, which is a 4. So you need to have a 4 here to get rid of. And since I don't, I'm going to rewrite this as 1/4, 0 to 1. Well, what happened? Extra 4, 4t plus 1 to the power of 5 dt. Okay, this is the reverse chain rule method. Then knowing this, of course, the 4 then disappears. Goodbye. We still have the 1/4 in the front, and then now we have 4t plus 1 to the power of 6 divided by 6. And then now we're going to evaluate this from, I guess, 1 to 0. This simplifies to 1 over 24. And then now I can plug it in. So 4 times 1 plus 1 to the power of 6 minus 1/4 times, right, 4 times 0 plus 1 to the power of 6. And I think this just becomes what? 1 over 24 times 5 to the power 6 minus 1 over 4. And this is just 1, so 1 over 4. So there's my answer. And once again, I'm not going to simplify. I'm just going to leave it like that. Okay. Now, for those of you who don't really like that weird reverse chain rule method, let me show you the u-substitution way as well for number 11. That's why there's some extra space here. So if I do the u-substitution method, remember the idea is that u equal to the stuff in the bracket. By the way, you don't need to write this both down. Choose whichever one you like. Do it. du dt in this case, of course, is 4, and that's why we get that factor of 4. Going to solve for dt now, remember. So dt equals to du over 4. Okay. Now we're ready to substitute. So now when I substitute, this expression becomes the integral, and our 4t plus 1 now becomes u to the power of 5. Our dt now becomes du over 4. And wait, what happens to our limits? Remember, these values of 0 and 1 represent t values. But when I'm doing a u substitution, I want everything to be in terms of u, and that includes those limits. So how do I figure them out? Yeah, substitute them in here anyway. So if I plug in 0 for t, 4 times 0 is 0 plus 1 is 1. My new lower limit is now 1. Similarly, if I plug in 1, 4 times 1 is 4 plus 1 is 5. My new upper limit is now 5. And so now you've changed everything, including the limits, to in terms of u. Let's go ahead now and anti-differentiate. Actually, I'm going to pull up the 1/4 first. Now I'll anti-differentiate. I forgot some equal signs, I'm sorry. Here we go. U to the power 6 over 6. Evaluate from 1 to 5. So once again, 1 over 24 u to the power 6, evaluating from 1 to 5. 1 over 24, 5 to the power 6, minus 1 over 24 times 1 to the power 6, which is, of course, just 1 over 24. I forgot that over here. My apologies. This should be 24. I wish you told me that earlier. Sorry, I know you can't. Thank goodness I did this twice. Woo! Because the answer is supposed to be the same. Alright, so once again, here's the fundamental theorem of calculus using a u-substitution example. Okay? Let's continue with 12 and 13. And you're like, oh no, I see more u-substitution examples. You got that right. So for number 12, let me quickly try u-substitution with you again. 2x minus 1. Remember, you need to solve for dx. I hope this is old hat for you now. So you've done so many examples. You're like, I got this, I got this, I got this. Yes, I know that was just the last week's homework or last day's homework. So I hope you did that. Okay. Oh, remember this case? Oh, well, maybe if you didn't. Nonetheless, we can go ahead and do the substitution. Okay. I will substitute the integral and the limits. So 2 times 1 is 2 minus 1 is 1. Plug in 5, that's 9. We have an x on the top. We have a root u in the bottom. We have du over 2. And we are stuck because we still have an x. Oh, no. Don't worry. Be happy. Because you can. That's right. Solve for x. Yay. So I will replace that x here with also u plus 1 over 2. Ooh, lots of 2's, 2's, 2's. Be careful, these 2's do not cancel each other out. They're both dividing by 2. So actually they can be combined together and pulled up to the front 1/4. And then I now have u plus 1 over root u du. And I will quickly write that in terms of powers. So dividing u divided by root u is just root u. I'm going to write this in powers, right? That's right. Let's write this in power form. U to the 1/2. And then now I'm going to do 1 divided by root u. And that just becomes plus u to the negative 1/2 du. And now you're set. Let's go ahead and take the antiderivative. We'll leave the 1/4 out front. This becomes u to the 3/2. Don't forget now 2/3. And then over here, this will be what? U to the 1/2, and then a 2 in front. And then let's see what we get. One quarter. Let's go and evaluate. We'll plug in the number 9 now. So 9 3/2. 2 times 9 to the 1/2 minus, we ran out of space, but nonetheless I'll do that. Oh, I'm going to put a big bracket around here too. That 1/4 applies to everything. 2/3 times 1 to the 3/2 plus 2 times 1 to the 1/2. We will simplify. 9 to the 3/2, square root of 9 is 3. 3 squared is 27. So 27 times 2 is 54 over 3. This is plus 6 because the square root of 9 is 3. Whoa. Minus, that's just 2/3 plus 2. Ooh, 1/4, 54/3 minus 2/3 is 52/3. 6 minus 2 is 4. This is getting really ugly. I don't really want to do this, but nonetheless I will because I'm doing it for you. 52 over 3. 4 in thirds is just 12 over 3. That's 64 over 3. So 1/4 times 64 over 3 is just 16 over 3. Wow. Woo. I'm tired. But nonetheless, that's how you do a question like this. See, I'm putting everything you've learned together so far in Unit 6 all into one question. Woo! Okay, 13. Let's finish that, and then I know there's one more topic. I'd probably advise you to take a break, and then we'll come back to finish off that last topic. Okay, example 13. I don't know which one do you want me to use, reverse chain rule or u-sub. Doesn't matter to me. I'll use reverse chain rule, okay? So using reverse chain rule, I see that I need a factor of the derivative of the bracket, which is a 2. So I will rewrite this as 1/2 on the outside. Here's now my 2, cosine 2x dx. This is great because now I can just take away the 2, goodbye. The integral of cosine, of course, is just sine. So this is now sine of 2x. Evaluate from pi over 2 to 0. I will do that now. Sine of 2 times pi over 2. Nice. Minus sine of 2 times 0. Nice. And don't forget that 1/2 applies to both of those terms. Why do I call that nice? Because sine of pi, oh, I like that. Sine of 0, I like that. Why do I like that? Because I love trig? No, I love 0. Yes. 0. Done. Okay, So that is using the fundamental theorem of calculus, which really is a method to allow us to calculate the value of a definite integral. The last examples here, 11, 12, 13, were complicated because we had to use u-substitution or reverse chain rule. Okay, take a break. Press pause. Grab something to drink. Come back. Okay? Okay, so the last thing that I want to talk about in this lesson is this thing called start plus accumulation. If you are doing the AP exam, star this, star this, star this, star this. I guarantee you will find a question on the AP exam that uses this thing called start plus accumulation. Okay? What is really the start plus accumulation? It's nothing new, because it's really the idea of the fundamental theorem of calculus mumble jumble mixed up. It really is this. If I were to take this f of a and stick it on the left hand side, notice I'll have f of b on the right hand side, and then I'll have f of a plus the integral from a to b of f prime of x dx. Why do I call this start plus accumulation? Because f of a here is like my start, like my starting value. I call the integral from a to b of f prime of x dx my accumulation. And then the ending here is f of b. So to get an ending value, f of b, end, right? That's equal to a starting value, f of a, plus some sort of accumulation value to get from start to end. Okay. So this means that a function value at an endpoint, right, the end, can be found as the starting value plus a definite integral. Okay? So once again, it's the slight variation. It's just taking the fundamental theorem of calculus and tweaking it. But once again, I've seen it almost every single year on the AP exam. So looking at number 14 here, I've given you the derivative. And notice I said f of 0 equals to 4. So this is like my start. And I want you to find the end. Okay? So that's the idea. Start and end, right? So what can we do? I would say go ahead and use this idea of start plus accumulation. So the ending value, f of 2, equals to the starting value, f of 0, plus the integral from 0 to 2 of the function, or of the derivative, 3x squared plus 3 dx. F of 0 we know is, 4. And then here we can just do the antiderivative, so that's x cubed plus 3x. And then we will evaluate this antiderivative from 2 to 0. Here we go, 2 cubed plus 3 times 2 minus, nice, 0 cubed plus 3 times 0, I like 0. And so 4 plus 8 plus 6 minus 0. And if you got 18, there you go. F of 2 is 18. Okay. Alright. Number 15. If an object's velocity is this. And s, remember that's the position function, is 8 at 1. Find s of 2. Same idea here, everybody. Just go ahead and here's my ending value. Here's my starting value. Add to it my accumulation from 1 to 2 of the function 2 to the power of 3t squared minus 5. And then don't forget notation, dt. Now, if you're going to try to anti-differentiate this by hand, I wish you good luck, because I don't even know what this is. So if you can't do it by hand, go and use the calculator. Use the calculator to figure that out for you. So s of 1, that's 8. Now use the calculator. Hello, calculator. We haven't seen you since the beginning of this lesson. Welcome back. I hope you had some fun. being by yourself. Here we go. Math number 9. Here's the function 2 to the power of bracket 3x squared. We'll just use x, right? It says t, but we can use x. Minus 5. Close the bracket once. Comma our variable x. Comma our starting or left limit 1. And our right limit or our upper limit 2. Close the bracket. Press enter and let it do its magic. 16.502. Perfect. 16.502. So our final answer for S of 2 is 24.502. Okay, there was a lot in this lesson as well. So once again, like what I always say, you've got to practice on your own. Listening to me and thinking that you understand things is great, but you're not really going to solidify your understanding until you do them yourself. Okay, it's practice time.